Okay, welcome back to my YouTube channel. I want to revise with you a question together with my student in here. So you must be collaborating by leaving some comment in the comment section below, and I'll be happy to reply to your comment. Okay, so this is from Radioactivity Physics. I hope you can see what is written here. The question is, in an experiment to determine the half-life of a radioactive element, the following results were obtained, and this table is representing the result which were obtained from this experiment. The first question A is, state what is meant by the half-life of a radioactive element. In other language, they are saying that define half-life. So what is half-life? Who can define half-life? Yes, please.
It's the time taken for the radioactive isotope to decay.
Yes, so half-life is the time taken for half of the radioactive isotope to decay to half. So I'll write here where I'll write the question, the answer. So half-life is the time taken for half of the radioactive isotope to decay. Okay, so that is what is called the half-life. So half-life of the radioactive element is the time taken for half of the radioactive isotope to decay. Go now to question B. Okay, first write the answer if I'm not written yet. Question B. From the results in the table, calculate two different half-lives. From the result given in the table there, we need to calculate two different half-lives. So we need to do the calculations here. We need to do the calculations. Add up those ones two copy on to wrap that. That's the only space we have for calculations. Okay, so now for you to calculate the two different half-lives, the first equation you need to use is N is equals to NO multiplied by 1/2 to the power N. You first have to find the number of half-lives which have passed through. You first need to find the half-life, the number of half-lives which have passed through. So the first half-life will be calculated from 0 to 110. Then the second half-life will be calculated from 0 up to 160. Okay, so let us find the half-life of the first part. So let us find the value of N. N is representing the amount of material at the start. All right, here. N is representing amount of material left. So material left. And the NO is representing the material at start. NO is representing the material at start, where the small letter n is the number of half-lives. So the number of half-lives. Okay, so the small letter n is the number of half-lives. Now, the amount of material left in the first 1/10 second is 250. So they are going to put 250, of course. 250 is equals to the amount of material at start, which is 1000. Okay, then multiply by 1/2 to the power n. Now you cannot multiply 1/2 times 1000 because of that formula we use in mathematics, the BIDMAS, where I stand for indices. So indices comes first in this formula. So we have the n to the 1/2 to the power n. So therefore you cannot multiply 1/2 times 1000 because of this power. Put the phone on vibration, Okay, so what you're going to do is, we are going to divide both sides by 1,000, even here by 1,000. 1,000, 1,000 goes. We have 1 over 2 to the power n is equals to, you can reduce this. How many times can 25 go there? 1. 25 in 200, how many times? 4. 4 times. So we have 1 over 4. Now you can simplify this using the indices. You'll find a number which you can power 1 over 2 to give you the same as 1 over 4. So in this case, I'll write it from here. What number can we power 1 over 2? Because in indices you relate that you can find this by making the base to be the same, isn't it? Yes. You have to make these two to have the same base. So what you are going to do is, we have 1 over 2 here to the power n. Even here we're going to have 1 over 2. But what number can you power 1 over 2 to get 1 over 8? It's 2. Okay, good. So you have 1 over 2 to the power 2. There we have the power n. Once you have the same bases, what do? You cancel them out, and you remain with 2 is equals to n, which is the same as n is equals to. Now that you have the number of half-lives which has passed through, you can easily calculate the half-life by using the formula number of half-lives passed is equals to time over the half-life. Half-life is represented by the small letter t with a subscript t, 1 over 2. What is the number of half-lives which have passed? 2. Okay, so we have 2 as the number of half-lives which has passed, which is equals to, what is the time taken for the first part? So I said that the first half-life will take from 0 to 110. So what is the time taken? 110. Remember, this is the time taken, is it? So we have 110 over the half-life. Okay, then you're going to raise this one as a fraction and cross multiply. You get that, eh? So when you cross multiply, you have 2 times 1 half-life. You have 2 half-life, which is equals to 1 times 110. We have 110. So to find the half-life, divide by 2, divide by 2. This one goes. The half-life is equals to, what we have there? 55 seconds. Eh? So the half-life, I'll put it here. The half-life is equals to 55 seconds. So the first half-life is 55 seconds. The first half-life is 55 seconds. Now let me stop it. Okay, please do it fast. Fast as we're cooking. Have we finished? Okay, now the second half-life. Remember the question is we need to find the two half-life, is it? Two different half-lives. So we need to do the similar procedure. We need to do the similar procedure. So the second half-life. So you first have to find the number of half-life which has passed through in the second event. So using the same equations which are from using, say n is equals to NO to the power 1/2 to the power n. Okay, then we have to find the value of n. N is the amount of material left, and NO is the initial amount of material at start. So what is n? Since it's the second half-life, meaning we're using the second time, is it? What is the amount of material left when it is 1/62? So we have 125 is equals to what is the amount of material at start? 1000. Okay, times 1/2 to the power n. Same thing is applying here. You cannot multiply 1000 times 1/2 because of the power there, is it? Indices comes first. So divide by 1000, even there by 1000. Then we have 1000 there, 1000 there. We have been left with 1/2 to the power n, which is equals to 125 here. It's 125 into 1000. We're getting the 8. Good. So we have 1/8. Now, when you reach there again, you need to use the idea of indices to find the value of n. We have to make these two to have the same base, and we can convert this one have the same base of 1/2. So what we can do is, what is 1/8? Yes, so we put 1/2, which is equals to 1/2 to the power n. Now we find the number to power 1/2 to get 1/8, which is the 3. Okay, so once you have the same base, you cancel them out. You remain with 3 is equals to n, so the same as n is equals to 3. Now that we have the number of half-lives which has passed through, we can calculate the second half-life. So the second half-life becomes n is equals to time taken over the half-life. What is the number of half-lives which has passed through? We have found it to be 3, which is equals to, what is the time taken? 160. So we have 160 over the half-life. Okay, then you raise this one as a fraction and the cross multiply. 3 times half-life, you have 3 half-life, which is equals 1 times 160, you have 160 itself. And you divide by 3, this one goes. The half-life is equals to, what do you have to divide this one there? 53.33 seconds. Okay, so the two different half-lives, the other one we found in the beginning, 55 seconds, and the second one is 53.33 seconds. So that's how we calculate the half-life. That's how we find the half-life. Okay, we go to Roman number 2. Go to Roman number 2. The questions are simple, isn't it?
Yes.
That's the issue of knowing the formulas. What to put on the formulas, that's all. From B1, yes. Yes, we are calculating 2. The question is 2 different half-lives. So the 2 answers are for the same question. We wanted the 2 different half-lives. Okay, we move on. Okay, now we find Roman number 2. the average half-life of the element. Okay, this one is easy, isn't it? Just find the average. How do we find the average? The average half-life, remember half-life 1, we had found 55 seconds, eh? Yes. Then half-life 2, we had found 53.33 seconds, eh? Yes. Okay, so to find the average, you add these two and divide by, because there are two which you are adding, isn't it? So the average half-life is equals to 55 plus 53.33. Then you divide by, we are dividing by 2 because we have added 2, is it? If we had 3 half-lives, we would have divided by 3. You get that, right? So if you add 55 plus 53.33, what are you getting? Is it 108.33? Yes. Divide by 2. 54.165. Okay, so the average half-life is 54.165 seconds. So the average half-life is 54.165 seconds. 54.1.2, 54.16 or 17. You can still round off, isn't it? Yes. Okay. Remove. Question C. The element thorium is radioactive. Now, it decays by emitting beta particle and has the half-life of 24 days. So this one, half-life has been given, isn't it? The half-life is 24 days. What is a beta particle? What is a beta particle? What is it? Stream of fast-moving electrons. Yes, a beta particle is a stream of fast-moving electrons. Okay, so a beta particle is a stream of fast-moving electrons. So for the question which I've already calculated, think of the rugby, but we should have enough space. So a beta particle is a stream beta particle is a stream of fast moving electrons. Is a stream of fast moving electrons. That's what is called a beta particle. Okay. To writing? Okay, question Roman number 2, C Roman number 2. Calculate the number of protons and neutrons in the nucleus formed when thorium emits beta particle. So we need to find the number of protons and neutrons in the new isotope which will be formed when thorium produces a beta particle. So you cannot find this one without writing the decay equation. You first have to write the decay equation, is it? So decay equation will be thorium, this was 234. Okay, so thorium 234 and 90 has produced a beta particle with the, what's the mass number of a beta particle? 0. Atomic number. Then to produce a new element which you don't know, is it? Okay, so we know it when we find first the number. So that would be 234 minus 0, that is 234. Then we have 90 minus negative 1, we have 91, isn't it? So the atomic number of the radioactive isotope always increases by 1 when it has produced a beta particle. You get that, eh? Yes. Okay, so you check on the periodic table the element with the atomic number 91, then use that symbol. So what is the element with the atomic number 91? What is the element with atomic number 91? PA, which is protactinum, isn't it? Okay, so we have PA, which is protactinum. Now, the question did not ask you to write the decay equation, but it required you to write this before you can calculate the protons in the new isotope that has been formed. So this is the new isotope which has been formed. So now we need to find the number of protons and the number of neutrons. So how many protons are in the new isotope formed? 91. Okay, so protons we have 91. Okay, then we find now the neutrons, isn't it? How many neutrons are there? 1. Okay, so you subtract the mass number minus the proton number. You can simply do this by making an equation where we say the mass number is equals to the proton number plus the neutron number. And the mass number is 234, which is equals to what's the proton number? 91. We don't know the neutron number, is it? So the atomic number, the proton number goes there, and this becomes 234. 91 goes there, becomes minus 91, which is equals to the neutron. So 234 minus 91? 143. Okay, is equals to the neutron. So therefore we have 143 neutrons. Okay. Quick. So we go to the Roman numeral 3 now. Roman numeral 3, calculate the time taken. Calculate the number of protons and neutrons in the nucleus of thorium. So in this case, we want the same nucleus of thorium. Now we need to find the number of protons and the number of neutrons. So how many protons are in thorium? 90. Okay, so protons are equals to 90. Then how many neutrons are there? Yes, neutrons is equals to, we have 234. 234 minus the proton number, which is 90, and the neutron number is equals to 144. Okay, as easy as that. We got the second last question. Okay, 5. Roman numeral 4, calculate the time taken for 1 gram of thorium to decay having 1/80 unchanged. Then how are we going to calculate that? You still need to use the same formula for half-life. Why do you have to use that? The half-life is given. You get that time. The only thing we need to do, we first have to find the value of the n again. Okay, so we find the value of the n by using the same equation. N is equals to the NO multiplied by 1/2 to the power n. What is the amount of material left? Who can guess the amount of material left? Amount of material left? 1/8. Good. So we are saying that 1 gram to decay to 1/8. So from 1 gram to 1/8. So the amount of material left is 1/8. So 1/8, which is equals to the amount of material at start 1, is it? At start, you are saying that it is 1 gram. So 1 multiplied by 1/2 to the power n. You know, any number divided by 1, it used to be the same number. Eh? So we have 1/2. 1 into 1/8, we still have 1/8, which is equals to 1 there, remain with 1/2 to the power n. Again, use the idea of indices to find the value of n, where you have to make these two to have the same base, of which you have 1/2 is equals to 1/2 to the power n. You find the number to power this 1/2 to get 1/8, which is 3. When you power 1/2 to the power 3, you're going to get 1/8, because 1 times 1 times 1 is 1, 2 times 2 times 2 is 8. So once you have the same base, you do what? You cancel them. 3 is equals to n. So n is equals to 3, isn't it? When you find the n, now we can find the time taken. Here we are not calculating the half-life. We are calculating the time taken. Half-life has already been given. You get that, right? So, but you're using the same equation where we said n is equals to time taken over the half-life. What is the n? The n is 3. So 3 is equals to, what is the, okay, time we don't have, what is the half-life? Half-life is 24 days. But we know that this element has half-life of 24 days. So where there is half-life, we have to put 24. Okay, we raise this one as a fraction and you cross multiply. This times that, what we have?
72.
Time is equals to 3 times that, 72 days, eh? 72 days. Okay, so the time taken is 72 days for it to decay from 1 gram to 1/8. But you can, okay, let me quickly solve that, but to show you the other way of finding it. Where I said sometimes you cannot even need this formula. You can use another way to find it. Are we done? The other way you can calculate this question is just by using a box where you have the mass given. In this case, we're using mass, isn't it? Here is the mass, and here is time. You see that, right? Now, when it is 1 gram, before the start, time is 0, isn't it? It has not yet started. But once it decays to half, it will take how many days? 24 days. So from 0 go to 24, what will be the mass there? What will be the mass? The half of 1, is it? Which is 1/2 or 0.5, right? Okay, again, if another 24 days, 24 plus 24 is what? 48. The half of 1/2 is what? 1/4. Again, after 24 days, that is 48 plus 24, what do we have? 72, is it? What will be the half of 1/4? 1/8. You see that then? So what is the time taken for it to decay to 1/8? It's 72 days. You see that? So can either use the formula or can go with this way. Either way, I'm going to the same thing. The same answer. Finally, the last question. No, this was an homework, eh? Should it still remain an homework?
No.
Okay. State one use of the beta radiation. One use of beta radiation. They are used in measuring thickness of materials. You get that, right? Beta radiations are used in measuring thickness of materials. Have you ever wondered how come they're able to make, the same thickness of this paper? I don't know for how many years I've been making this. How come pharmacy and circle, like they made a mistake to say, okay, this one is thicker than this? You see? So it's because of the beta radiation which detect that, okay, this is the same amount which has been put into this machine and seal off. So the beta radiation are used to measure the thickness of materials, like the thickness of the paper, the thickness of aluminum, and other things. Okay, so that's all. Unless you have other questions? No questions, isn't it? Okay, so this is the end of this question. If you have more questions, you can leave them in the comment section below. I'll be happy to respond to your questions, and have a good day. You